Good afternoon, students. I would like to complete problem number 2 with you today, and this is on activity 3.2.6, orbital mechanics. So I've had a few questions on the units, and so I would just like to work the problem for you today. So I'm going to read the problem. I'm going to underline some important information. We're going to develop a column of knowns and unknowns, and we're going to draw a simple picture to help us solve the problem. So let's get started. At what distance from the Earth's surface is a 10,000 kilogram satellite if its gravitational potential energy is equal to negative 5.58 times 10 to the 11th joules? Okay, now let's take a look here. It says what distance from Earth's surface. So what that's really asking us is for the altitude. What is the altitude of the satellite? And remember that altitude is identified by d sub 0. So that is our unknown. The mass of the satellite is 10,000 kilograms. And our gravitational potential energy, identified by capital U, is equal to negative 5.58 times 10 to the 11th joules. Now what we need to do here is go ahead and draw a simple picture to help us with the problem. So this is the radius of the Earth, identified by r sub e, and then we have the altitude of our satellite, identified by d sub 0, and the sum of both of these values is the center to center distance, so the center of the satellite to the center of the Earth, and this is identified by capital R. Now, our base equation for the gravitational potential energy is U equals negative universal gravitational constant times the mass of the satellite times the mass of the Earth. And we're going to divide this by R. Now earlier I mentioned R is the sum of the altitude and the radius of the Earth. So let's go ahead and expand our denominator here and write d sub 0 plus r sub e. Okay? Now this is what we are trying to calculate. This guy right here. So what we're going to have to do is a couple of algebra steps to isolate the altitude. First thing I want to do is multiply both sides by the altitude plus the radius of the Earth. So when we do that, on the right hand side, they cancel, okay? On the left hand side of the equal sign, we're going to have d sub 0 plus r sub e multiplied by the gravitational potential energy is equal to negative universal gravitational constant times the mass of the satellite multiplied by the mass of the Earth. Okay? Now, we're looking for this guy. So, we have two more steps. Our first step is to divide by the gravitational potential energy on both sides of the equal sign. Okay? On the left-hand side, that will go ahead and cancel. And so we're left, on the left-hand side of the equal sign, we are left with the altitude plus the radius of the Earth. So to isolate the altitude, all I'm going to do is subtract the radius of the Earth from both sides of the equal sign. And this is going to give me altitude is equal to negative universal gravitational constant times m sat times m Earth divided by gravitational potential energy minus the radius of the Earth. Okay? So what I want to do is start filling in values, and then we're just going to do our algebra step by step. So in my numerator, negative universal gravitational constant is 6.67 times 10 to the negative 11th meters cubed per kilogram seconds squared. Then we have mass of the satellite, and the problem tells us that it's 10,000 kilograms. Okay? Then we have mass of the Earth. This is 5.98 times 10 to the 24th kilograms. And we're going to divide all that by the gravitational potential energy, which is negative 5.58 times 10 to the 11th joules. And then we're going to subtract the radius of the Earth, so minus 6,378,000 meters. Okay? All right, so I'm kind of running out of room here, so I'm going to start erasing. Okay, so what I want to do right now is just take care of the numerator, and I just want to talk about the numerical value first, and then we're going to take a look at the unit value. So let's go ahead and get out your calculator. So our universal gravitational constant times 10,000 kilograms multiplied by the mass of the Earth is going to give me a negative 3.9886 times 10 to the 18th. So a very large value here, okay? But now let's take a look at our units. So I have meter cubed per kilogram second squared times a kilogram times a kilogram, so that's kilograms squared. And we can also write that as kilograms squared over 1. We can immediately see that one of our kilograms is going to cancel out, giving us kilogram meters cubed per second squared. Okay? Now, we're dividing this by our gravitational potential energy, negative 5.58 times 10 to the 11th. But let's not keep the unit in joules. Let's break down the unit of joules. So we know a joule, so 1 joule is equal to 1 Newton meter. We know a Newton is equal to a kilogram meter per second squared, and we're multiplying this by 1 meter, so meter over 1. So when we multiply this here, what we get is kilogram meter squared per second squared. Okay? So we need to write this. We need to write these units in the denominator right here. So I've got kilogram meter squared per second squared. Okay? And let's not forget that we are going to subtract the radius of the Earth here. So minus 6,378,000 meters. Okay? What I want to do is divide here. Let's talk about the numerical value first. Okay? And so I get 7,148,136.2. Now let's take a look at our units. Whenever we divide fractions, it's like multiplying by the inverse of the denominator. So I have kilogram meters cubed per second squared times the inverse of our denominator is going to be second squared divided by kilogram meters squared. Now, we can see that our second squared will cancel. Okay? Now let's take a look at our kilograms. I've got a kilogram in the numerator and a kilogram in the denominator. So our units of kilograms go ahead and cancel. Then I have meters cubed in the numerator and meters squared in the denominator. So we're left with units of meters. Now we need to subtract the radius of the Earth, 6,378,000 meters. And since we have like units here, we can subtract here. So let's subtract the radius of the Earth, 6,378,000 meters. And this gives me D sub 0, so remember this is altitude, 770,136.2 meters. Okay. All right, I tell you what, if you have any questions about problem number 2, please let me know. Go ahead and send me an email, and I hope you have a wonderful day.